Welcome. Today we're diving into the world of mesh analysis, fundamental technique in electronics for solving complex circuits. Whether you're a student, hobbyist, or professional, understanding mesh analysis can simplify your approach to circuit problems. In this video, we'll break down the basics, walk through practical examples, and give you the confidence to tackle any mesh circuit. Let's start by understanding what mesh analysis is and why it's so widely used in electrical engineering. Ready to power up your circuit solving skills? Let's get started. Before we jump into the analysis, let's clarify what a mesh actually is. In circuit theory, a mesh is a loop that does not enclose any other loops within it. Think of it as the simplest closed path in a circuit. Identifying meshes is the first step in mesh analysis, and it's crucial for setting up the equations you'll need. By focusing on these basic loops, we can systematically solve for unknown currents in even the most complicated circuit. Let's see how to spot meshes in a typical circuit diagram. Mesh analysis is a powerful tool because it streamlines the process of finding unknown currents in planar circuits. Instead of writing equations for every component, you focus on the loops, which often leads to fewer equations and a clearer path to the solution. This method is especially useful for circuits with multiple loops and shared components. By applying mesh analysis, you can save time and reduce errors, making it a favorite among engineers and students alike. Mesh analysis is best suited for planar circuits, those that can be drawn on a flat surface without any wires crossing. Most basic circuits you'll encounter are planar, which makes mesh analysis widely applicable. If a circuit isn't planar, other methods like nodal analysis might be more appropriate. Understanding the type of circuit you're dealing with helps you choose the right analysis technique and avoid unnecessary complication. Let's get familiar with some key terms. First, a mesh is a simple loop, as we discussed. Next, mesh current is the hypothetical current that flows around each mesh. These mesh currents are what we solve for using mesh analysis. Finally, Kirchhoff voltage law, or KVL, is the backbone of this method. KVL states that the sum of voltages around any closed loop in a circuit is zero. These concepts form the foundation of mesh analysis. Kirchhoff's voltage law is essential for mesh analysis. It tells us that the algebraic sum of all voltages in a closed loop is zero. This means that as you travel around a mesh, the total voltage gained and lost must balance out. KVL allows us to write equations for each mesh, setting the stage for solving the unknown currents. Mastering KVL is a must for anyone working with electrical circuits. Now let's practice identifying meshes in a circuit. Start by looking for the smallest loops that don't contain other loops. In a simple circuit with 3 resistors forming a triangle, each side is part of a mesh. Mark each mesh clearly, as this will help you assign mesh currents and set up your equations later. With practice, spotting meshes becomes second nature, making the analysis process much smoother. Once you've identified the meshes, the next step is to assign mesh currents. These are imaginary currents that circulate around each mesh, usually in a clockwise direction for consistency. Assigning mesh currents is crucial because these are the variables you'll solve for. Label each mesh current clearly on your circuit diagram to avoid confusion as you write your equations. Mesh currents assigned, it's time to write the KVL equations for each mesh. Start at any point in the mesh and sum the voltage drops and rises as you move around the loop. Remember, resistors cause voltage drops proportional to the current through them, while voltage sources add or subtract voltage depending on their orientation. Each mesh will have its own KVL equation, and together these equations form a system you can solve. Let's walk through a simple example. Imagine a circuit with 2 meshes, each containing resistors and a shared resistor between them. Assign mesh currents I1 and I2. Write KVL for each mesh, accounting for the shared resistor by considering the difference between I1 and I2. This example shows how mesh analysis handles shared components and sets the stage for more complex circuits. Once you have your KVL equations, it's time to solve for the mesh currents. This usually involves simultaneous equations, which you can solve by substitution, elimination, or using matrices. For small circuits, manual calculation works fine. For larger circuits, you might use a calculator or computer software. The key is to stay organized and check your work as you go. After solving for the mesh currents, interpret your results in the context of the circuit. Positive values mean the current flows in the direction you assumed, while negative values indicate the opposite. Use these currents to find voltages across components or total current in the circuit. Mesh analysis not only gives you the answers but also deepens your understanding of how currents flow in complex networks. Mesh analysis is straightforward, but there are common pitfalls. Forgetting to account for shared resistors, mixing up current directions, or making sign errors in KVL equations can lead to incorrect results. Always double-check your mesh assignments, current directions, and the signs in your equations. With careful attention, you'll avoid these mistakes and get accurate solutions every time. Mesh analysis isn't the only method for circuit analysis. Nodal analysis focuses on voltages at circuit nodes instead of mesh currents. Each method has its strengths. Mesh analysis is great for planar circuits with fewer meshes, while nodal analysis excels in circuits with many nodes or voltage sources. Knowing when to use each technique is a valuable skill for any electronics enthusiast. But if your circuit has a current source? In mesh analysis, current sources can complicate things. If a current source lies on the border between 2 meshes, you can use the concept of a supermesh. This involves combining the 2 meshes into one larger loop, bypassing the current source and writing equations accordingly. We'll explore supermeshes in more detail soon. Supermesh is created when a current source is shared between 2 meshes. Instead of writing separate KVL equations for each mesh, you combine them into a supermesh and write a single equation that bypasses the current source. You'll also need an extra equation to account for the current source itself. Supermeshes help you handle circuits with current sources efficiently. Let's look at a practical example. Suppose you have two meshes with a current source between them. Combine the meshes into a supermesh, write the KVL equation for the supermesh, and add an equation for the current source. Solving these equations gives you the mesh currents just as before. Supermeshes are a handy tool for more complex circuits. Sometimes, circuits include dependent sources, sources whose values depend on another current or voltage in the circuit. Mesh analysis can handle these as well. When writing KVL equations, express the dependent source in terms of mesh currents or voltages. This might add complexity, but the process remains systematic and manageable. Let's try an example with a dependent source. Suppose a voltage source in your mesh depends on the current in another branch. When writing your KVL equations, substitute the expression for the dependent source in terms of the relevant mesh current. This keeps your equations consistent and solvable, even with the added complexity. Mesh analysis works for circuits of any size, but large circuits can get unwieldy. For bigger problems, stay organized by labeling all meshes and currents clearly. Use systematic methods for writing equations and consider using matrix notation or computer tools to solve them. Staying methodical helps you avoid mistakes and saves time. For circuits with many meshes, solving the equations by hand can be tedious. That's where matrices come in. By expressing your system of equations in matrix form, you can use linear algebra techniques or software to find the solution quickly. This approach is especially useful in engineering and research settings. Mesh analysis isn't limited to DC circuits. You can apply the same principles to AC circuits using impedances instead of resistances. The process is similar: assign mesh currents, write KVL equations, and solve for the unknowns. Just remember to use complex numbers for impedances and currents in AC analysis. Mesh analysis is used in a wide range of applications, from designing electronic devices to troubleshooting circuits. Engineers rely on it to predict circuit behavior, optimize designs, and ensure safety. Whether you're working on audio equipment, power supplies, or embedded systems, mesh analysis is a valuable tool in your toolkit. When a circuit isn't working as expected, mesh analysis can help you pinpoint the problem. By calculating expected currents and comparing them to actual measurements, you can identify faulty components or wiring errors. This systematic approach saves time and increases your chances of a successful repair. During the design phase, mesh analysis helps engineers predict how a circuit will behave before it's built. By simulating mesh currents and voltages, you can optimize component values, improve efficiency, and ensure the circuit meets its specifications. This proactive approach leads to better designs and fewer surprises during testing. Mesh analysis is a staple in electronics education. It's often one of the first techniques students learn for circuit analysis, providing a solid foundation for more advanced topics. Practicing mesh analysis builds problem-solving skills and deepens your understanding of electrical principles. Modern simulation tools like SPICE use mesh analysis algorithms to solve circuits virtually. By modeling your circuit in software, you can quickly test different configurations and see the results without building anything physically. This saves time and resources, making mesh analysis even more powerful in the digital age. Researchers use mesh analysis to study new circuit topologies and develop innovative electronic devices. By analyzing mesh currents, they can predict performance, identify potential issues, and refine their designs. Mesh analysis remains a cornerstone of circuit research and development. While mesh analysis is powerful, it does have limitations. It's best suited for planar circuits and can become cumbersome for circuits with many meshes or non-planar layouts. In such cases, nodal analysis or computer-aided methods might be more efficient. Understanding these limitations helps you choose the right tool for the job. Non-planar circuits where wires cross in the diagram are not ideal for mesh analysis. These circuits require more advanced techniques or computer tools for analysis. If you encounter a non-planar circuit, consider using nodal analysis or specialized software to handle the complexity. Mesh analysis can be combined with Thevenin's theorem to simplify complex circuits. By reducing parts of a circuit to their Thevenin equivalent, you can make mesh analysis easier and more manageable. This combination is especially useful for analyzing circuits with multiple sources or loads. Similarly, Norton's theorem can be used alongside mesh analysis to further simplify circuit analysis. By converting parts of a circuit to their Norton equivalent, you can reduce the number of meshes or simplify the equations. This approach is particularly helpful in circuits with parallel branches. Mesh analysis isn't just for finding currents. You can also use it to calculate power dissipated in resistors or delivered by sources. Once you know the mesh currents, use Ohm's law and power formulas to find the power in each component. This is essential for designing safe and efficient circuits. Safety is a top priority in electronics. Mesh analysis helps ensure that currents and voltages stay within safe limits, preventing overheating or damage. By accurately predicting circuit behavior, you can design safer systems and avoid costly failures. Embedded systems often include complex circuits with multiple loops. Mesh analysis is a valuable tool for engineers designing these systems, helping them optimize performance and ensure reliability. Whether you're working on microcontrollers, sensors, or communication modules, mesh analysis can streamline your design process. Communication circuits like those in radios and networking equipment often rely on mesh analysis for design and troubleshooting. By understanding how currents flow through different paths, engineers can optimize signal strength, minimize interference, and improve overall performance. Power electronics, such as converters and inverters, involve complex circuits with multiple loops. Mesh analysis helps engineers predict current distribution, optimize efficiency, and ensure safe operation. This technique is essential for designing reliable power systems. Analog circuits like amplifiers and filters often use mesh analysis during the design phase. By calculating mesh currents, engineers can fine-tune component values and achieve the desired performance. Mesh analysis remains a go-to method for analog circuit design. While digital circuits primarily use logic gates, mesh analysis can still play a role in the supporting analog circuitry, such as power supplies and signal conditioning. Understanding current flow in these sections ensures reliable operation and prevents issues like voltage drops or overheating. Modern vehicles are packed with electronic circuits from engine control units to infotainment systems. Mesh analysis helps automotive engineers design and troubleshoot these circuits, ensuring safety, reliability, and performance on the road. Renewable energy systems like solar panels and wind turbines use mesh analysis to optimize power distribution and ensure efficient operation. By analyzing mesh currents, engineers can maximize energy output and maintain system stability. Robots rely on complex electronic circuits for control and power. Mesh analysis helps robotics engineers design circuits that deliver precise currents to motors, sensors, and controllers, ensuring smooth and reliable operation. Internet of Things (IoT) devices often feature compact, intricate circuits. Mesh analysis is invaluable for optimizing power consumption and ensuring reliable connectivity in these devices, which are becoming increasingly important in our daily lives. Let's review the key steps in mesh analysis. First, identify all meshes in the circuit. Next, assign mesh currents, usually in a clockwise direction. Write KVL equations for each mesh, accounting for shared components and sources. Solve the system of equations for the mesh currents. Finally, interpret your results and apply them to the circuit. With practice, these steps become second nature. Congratulations, you've now mastered the basics of mesh analysis in electronics. This technique is a powerful tool for solving circuit, designing new systems, and troubleshooting problems. As you continue your journey in electronics, keep practicing mesh analysis and explore more advanced topics like nodal analysis, Thevenin's and Norton's theorems, and computer-aided design. The more you practice, the more confident you'll become in tackling any circuit challenge.